So we're starting actually Calc-B now, and if I start with a function given f of x is equal to 6x cubed, one of the first goals we have is to find another function which we're going to call capital F of x, such that the derivative of capital F of x is equal to f of x. And if you kind of work your way backwards from what we've been doing, you should arrive at something like f of x is equal to, well, I'm going to want to do something. I'm going to definitely want to increase the power of x. So I'm going to increase it to an x to the fourth, and then I'm going to divide by that 4. So that way, if I were to take a derivative, it would cancel out the 4 in the denominator. So I get 3x to the fourth over 2. And this is called, this 3x to the fourth over 2 is what we call an antiderivative. We're not going to use that word a lot, but we are going to use it right now. And I say it is an antiderivative. It is not the antiderivative of f, because I could also do another function, f1 of x is equal to 3x to the fourth over 2 plus 5, and that would also be an antiderivative of f. And there are an unlimited number of these things that we can do. So this word antiderivative refers to any of these functions that if I take the derivative, I get the function that I started with. A function f is an antiderivative, which I'll abbreviate for you, of little f on an interval I if capital F prime of x equals little f of x for every x in that interval. So if I'm looking at functions that are not antiderivatives of the one we just did, I could potentially look at, I could make like an f2 of x equals 3x to the fourth over 2 plus another x. And clearly you can see that that is not an antiderivative of f of x equals 6x cubed. But if I wanted to do like an f3 of x and make this so that this kind of could represent anything, the standard in calculus is to say plus c, where c is a constant. Constant is a word that means unchanging. So c could represent any real number that you could possibly think of, where c is a constant. And if that's true, then f3 of x is an antiderivative. So one theorem that we're going to use that to prove, and this is important because some of you are wanting to take vector calculus next year, and if I make a theorem, you guys need to start to learn some techniques of proof. Given f is an antiderivative of little f on interval I, and given that g is an antiderivative of f on that same interval, given that f is an antiderivative on that, I'm moving this down here, my bad. G is an antiderivative of f if and only if, and I'm not going to use that notation so much as I'm going to use the double arrow notation. My condition is to say that g is an antiderivative of f if and only if big G of x is equal to big f of x plus some c, meaning that g of x and f of x differ by some value c, where c is a constant. And so the things that you have to use in this are the definition of an antiderivative and kind of what this shows. So this bidirectional arrow is important because it means that the if-then works both ways. So I can say if-then goes this way and it goes this way. Now, the proof of this, if g is an antiderivative, And so I have to do the proof in the first direction. If g is an antiderivative, and I'm going to prove the forward direction right now, so g is an antiderivative means that g of x is equal to f of x plus c. If g is an antiderivative, we're going to let h of x equal the difference between g of x and f of x. This is not necessarily an intuitive thing, but I'm going to let h of x equal that difference. And my if I do h prime of x, g of x and f of x both have the same derivative, so they both become, little f of x, and that difference is equal to 0. Well, for any 2 points, A and B, where A is less than B, in the interval I, so A and B are points in that interval, and A is just smaller than B. A is actually an x-coordinate. We can say that H is continuous on AB and differentiable on the open interval AB. Continuous on the closed and differentiable on the open. This should look familiar. By mean value theorem, there exists a C such that h prime of C is equal to the average rate of change, h of B minus h of A over B minus A, which is equal to 0. And if that's true, then h of B is equal to h of A, because that makes the numerator equal to 0. So if that's true, then h is a constant function of, or h is a constant function. We can just say that it's constant function c. It's just a constant. That means that g of x minus f of x is equal to c, because h is g of x minus f of x. So that means g of x is equal to f of x plus some c. So that all was just the forward direction. Let me pause and help another student. The reverse direction is far easier. For the reverse direction, I am starting, let's go back up here, I'm starting with the condition, that g of x is equal to f of x plus c, and I'm proving that g is an antiderivative of f. So this is the backwards direction. If g of x equals f of x plus c, and f prime of x is equal to f of x, little f of x, well then g prime of x is equal to f of x plus 0. So g prime of x is equal to f of x. So g prime of, so g of x is an antiderivative of f. Is an antiderivative. Because I proved it both ways, I can put a QED at the end, which means quod erat demonstratum, and thus it is shown, and I've proven that theorem that I just stated. The theorem's a pretty obvious one, but it's one worth kind of noting to start to prove some things. Okay, let's do some examples of antiderivatives. If y prime equals 3x, let's find y. We say y is equal to, well, what I'm going to do is this process where I take the exponent of 1, I increase it by 1, so I get x squared, and then I divide it by that 2, and I keep the constant of 3 in front, so I just put that, but don't forget the c, that's incredibly important. This is called the constant of integration. I said we wouldn't be using this term's antiderivative for very long. We're actually going to use a different symbol, one you've probably seen before. So if I say dy dx is equal to f of x, and it's sort of standard to use a lowercase f of x to represent a function, and then an uppercase to represent its antiderivative, and then I multiply that both by dx, I get dy is equal to f of x dx. And this equation leads to another result. I'm going to do an integral of both sides, what's called an integral, and that means that y is equal to the integral of f of x with respect to x, or dx, and that's equal to capital F of x plus c. So let's kind of label these parts here, because this is going to be very, very new for several of you, at least in all these things. This will become exceedingly familiar, but this symbol here is called an integral symbol, the opposite of derivative. This thing afterwards is called the integrand. It's the thing you're taking the integral, just like radicand. And the dx indicates the variable of integration. And you only integrate across one variable at a time. F of x here is called an antiderivative of f, and c is called the constant of integration. I might do a quiz where I ask you guys to label these parts, because you need to know this terminology so that we can all speak the same language with this. Okay, number 2, we're going to do the integral of 8x with respect to x. Never, ever, ever write an integral of a function without the variable that you're integrating about. So, well, one of these things is I have this constant multiplier rule. This was the same as it was before, so I can actually say that that's the same as 8 times the integral of x dx. And the integral of x, if I treat that as x to the first and then raise that to the second power, that's going to become 8 times x squared over 2 plus a constant, and that's just the same as 4x squared plus that constant. Okay, number 3. We're going to do the integral of 1 over x to the 5th dx, which you might see sometimes as the integral of dx over x to the 5th, just to consolidate it. Probably best to rewrite that as the integral of x to the negative 5th dx. And then do the same thing. Take your exponent, increase it by 1, so that becomes x to the negative 4th, and then divide it by that same negative 4. And then don't forget your constant. And then the last step is just a cleanup step. So it's probably best expressed as negative 1 over 4x squared, or sorry, 4x to the 4th, and then plus a c. Number 4, I'm going to do the integral of the cubed root of x dx. A dx should not appear under the radical. It's just off to the side. This is probably one where I also want to rewrite it as x to the 1/3 power times dx. Then you're going to increase 1/3 by 1, so I get x to the 4/3, and then divide it by 4/3, which you don't have to write it like that, but I'm going to right now. Also put the plus c at this moment, and then clean it up a little bit. 3x to the 4/3 over 4 plus c. 5, I'm going to do the integral of 3 cosine of x dx. Constant multiplier pulls the 3 out, and I just get the integral of the cosine x dx. And the antiderivative of cosine, the thing whose derivative is cosine, is sine. So this just becomes 3 sine x plus a c. Next, number 6, we got the integral of x cubed minus 4x squared plus 1 dx. And you're just going to do each part separately. So this is going to be raise the 3 by 1, x to the 4th over 4, minus raise the 2 by 1, 4x to the 3rd, divide by that same 3. And then the integral of 1 is just x, and then plus a c. Seven, we're going to do the integral of 2x minus 1 over root x dx. So this is a case where you want to first rewrite this. So I'm going to divide this into both the numerator. So I get 2 root x minus 1 over root x dx, which is the same as 2x to the 1/2, keeping this in parentheses, minus x to the negative 1/2 dx. Now we're going to integrate each part separately. Keep the 2 off to the side. That's the constant multiplier. X, raise it by 1. We get 3/2. And then divide by 3/2 is the same as multiplying by 2/3. So I'm going to stick that 2/3 like that. Minus, we're going to increase that by 1, so that becomes x to the positive 1/2. Then divide by 1/2 means multiply by 2. And then plus c. The cleanup here is just going to look like this. I get 4 x to the 3/2 over 3 minus 2x to the 1/2 plus c. There's not much more you can do with that. I mean, you could feasibly factor a, out of this, you could factor in a root x out. And so if I factor a root x out, I'm going to get 4x over 3 minus 2 plus c. But that's not really that helpful because I still have that plus c. So I would probably just leave it the way it is, like this, because that's a descending order polynomial in a sense. Okay, last one, number 8, the integral of sine x over cosine squared x dx. Well, we're going to have to somehow change this into something right now that we know what the integral is, because doesn't matter if I know the parts of it, I need to see the whole. One of the ways I can do that is by doing a changeover and rewriting this as the sine x over cosine x times 1 over cosine x, and then changing each of those parts into the tangent x secant x dx. And if you remember your derivatives, the derivative of secant is secant tangent. So this is secant x and then plus c. That is it. The homework for you, at least in 2017, not sure when future people might be watching this, but this is for 1 through 8 all and 15 through 43 odd. Enjoy.